Howdy, students. In the last video, we added an atmosphere to our climate calculation and found that an atmosphere warms the planet. Conceptually, this occurs because on a planet with an atmosphere, the surface is heated not just by sunlight, but also by radiation from the atmosphere. It is this warming of the surface by the atmosphere that we mean when we talk about the greenhouse effect. Now, we call this a one-layer problem because the atmosphere is represented by one layer. In this video, we'll do another calculation, this time of a two-layer atmosphere. The idea of a layer may be a bit opaque, but you can think of how many layers an atmosphere has as how thick the atmosphere is. The more layers there are, the better the atmosphere is at absorbing infrared photons. As we'll talk about at some depth in Chapter 5, greenhouse gases are the component of the atmosphere that absorbs infrared photons, with carbon dioxide being the most well-known. The amount of greenhouse gases in the atmosphere therefore determines how well an atmosphere absorbs infrared radiation, and therefore determines how many layers there are. So you can consider this two-layer problem to represent an atmosphere with more greenhouse gases in it than a one-layer atmosphere we did in the previous video. So let's calculate the surface temperature of a two-layer atmosphere. Okay, so we're going to do the two-layer atmosphere and calculate the surface temperature. So again, the first thing you do is draw a figure and make sure you put in all of your fluxes. So it's a two-layer model, so here's the ground. Here's the bottom atmospheric layer, and here's the top atmospheric layer. Here's the sun, and so let's put our fluxes in. Okay, so sunlight goes through the atmosphere and goes to the surface. And again, that's our assumption that the atmospheres are transparent to visible radiation. The surface, it radiates up, and all of those photons are absorbed by the atmosphere because the atmospheres are not transparent to infrared radiation. They absorb all the infrared radiation. This atmospheric layer, it radiates up and it radiates back down. Now, the photons that are radiated down, those get absorbed by the surface. The photons that get radiated up, those get absorbed by the upper layer, because remember, the layers absorb all the infrared photons. So this upper layer is absorbing all of the photons that are coming up. Now, this upper layer also radiates like a black body in both directions. It radiates up, that's out to space, and then it radiates down back to the layer below it. Okay, so now that we have our diagram, we have all our flux arrows, let's go ahead and start putting some numbers on there. Okay, so first thing to do is to calculate energy in. Now again, that's the equation we want to use is energy in equals S times 1 minus alpha over 4. S is a solar constant, alpha is the albedo. This is the Earth. So we know the values are 1360 and 0.3, and that gives us 238 watts per meter squared. And that's energy in. So we know the value of this arrow right here. Again, that's the same for the previous examples we've done. So watch those videos if you want to make sure you know where that number comes from. So now what we want to do is we want to start at the top of the atmosphere and move down. And we want to apply energy balance to each of these elements. So the first thing we want to do is planetary energy balance. We have energy in is 238 watts per square meter, so energy out to space has to also be 238 watts per square meter. Now, all of the energy to space is coming from this arrow because all of the photons that are being emitted are coming from the upper layer of the atmosphere. So we immediately know this has to be 238 watts per square meter. So this is exactly the same thing we did with a one-layer planet. Now, because the atmosphere radiates symmetrically, up and down have to be equal. That immediately tells us that this one has to also be 238 watts per square meter. So far so good. Now comes something which is a little bit trickier, and that is, what is this arrow right here? Well, you know that energy in has to equal energy out, not just for the planet as a whole, but for each individual element. So energy in has to equal energy out for this atmospheric layer. Now we know what energy out is. It's 238 up and it's 238 down. That's 476.
And so energy in for this layer has to equal 476. The question is, where is energy in coming? Well, it's all coming from this arrow right here. All of the energy for this layer is coming there. So that means this arrow has to be 476. And then by symmetry, this down arrow also has to be 476 because the radiation up and the radiation down have to be the same. Okay, so this last arrow. All right, so for the surface, much like the atmosphere here, the surface here has to have energy in equal energy out. That's terrible. So energy in is 476 plus 238. That is 714. Hopefully I did not make a math mistake. And so energy out, 714, equals energy in, 476 plus 238. Now, we can check, and you should always do this, to make sure that energy in equals energy out for everything. So for example, if we come here to this top layer, energy in is 476, energy out is 476. Check. Now, we haven't done this one, but energy in has to equal energy out for this layer. So for this layer, energy in is 714 plus 238. Energy out is 476 up and 476 down. So 714 plus 238 has to equal 476 plus 476. And it will equal. Work it out. And then finally for here, energy in 476 plus 238, energy out 714. So that should match also. So we've balanced all the fluxes, and we've gotten our diagram completely written out. So now we can calculate the surface temperature. Okay, so remember, we calculate the surface temperature because we know what the surface is emitting. So 714 watts per meter squared is equal to sigma T to the fourth. Okay, Stefan-Boltzmann law. So you should now be able to solve this for T. If you do that, you'll get T equal 335 Kelvin. And there, you've calculated the temperature of a two-layer planet.
So let's summarize. With no atmosphere, the surface temperature of the Earth-like planet was 255 Kelvin. If we add a one-layer atmosphere, the temperature rises to 303 Kelvin. If we add a two-layer atmosphere, the temperature rises to 335 Kelvin. Now, we can generalize this to an n-layer atmosphere, where n is some arbitrary number of layers. This is the figure for the book, and I'm not going to go over the derivation, so read the book and make sure you follow it. But I will give you the solution. This is it. This is the equation that gives you the surface temperature of an n-layer planet with solar constant S and albedo alpha. Make sure you know this equation. You're going to be using it a lot in the rest of the class. Now, this is an amazing equation. Just a few weeks ago, you came into class not knowing anything about the climate, and now, learning just a few simple physical principles, we have an equation that tells us that the climate is determined by three factors: the solar constant, the albedo, and the number of layers. As I said before, the number of layers is determined by the amount of greenhouse gases in the atmosphere. If any of these parameters change, we expect the climate to change. As we'll see in Chapter 5, we are adding greenhouse gases to the atmosphere. So just based on simple physics, we expect the climate to be warming because N is increasing. And indeed, as we saw in Chapter 2, the climate is warming. In the next video, we'll test this equation on the planets in our solar system to see if the equation holds up. Spoiler alert, it does. And now, your moment of dog.